So as I find myself on the glide path to retirement, I get a little bit antsy. These incredible pictures from HST, especially of the preplanetary nebulae, are trying to talk to us and we're not listening. So in the course of the last 6 months, and with help from some folks up in here, I have had just a blast running hydro models. This talk is about the hydro models that we run, but it's primarily a review of hydro models over the last decade. A lot of them have been hiding in the literature, perhaps not well enough known, and I'd like to shed some light on these. They're very, very interesting. Now, before I go on, Adam, well, there's a saying in the Talmud, no one will correct me if I'm wrong. You learn from your teachers, you learn more from your peers, and you learn the most from your students. This collaboration with Adam, who's a former student, and Martine, who's a postdoc with Adam, and Kira, who's an undergraduate working with me, has just been incredibly rewarding, and I'd like to thank all of them. About a year ago, I thought, what we should do is cull through all of the HST images and find a set that nicely represent the sorts of shapes that are seen. Now, here I'm talking about those that have two lobes, with perhaps something in between them, not just a gap. And those become a set of targets for hydro models and for additional observations as well. So here they are. They all have names. I'm not going to review them. The symmetries are stunning. Some are cylindrical. Many of the lobes are closed. A few are open. And that's telling us there's a physical process here that shouldn't be that hard to understand. Now, before I get into the lobe shaping, I'd like to mention a couple of things about launching mechanisms. Really, that's the name of the game. And Adam and his group have been working on MHD launch mechanisms illustrated here. You saw pictures of these earlier this week. These are the magnetic towers. So basically, pointing dominated flux comes up, it becomes a bit unstable under certain conditions, breaks up, can break up into knots, and out they go. This is something which got to me last week. This is another launching mechanism. The size scale here, that's 100 AU. There's an imposed magnetic field, which I don't think we would find in and around preplanetary nebulae. The field lines guide the winds that come out from the central star. They run along the edge of this eye and then squirt out. And the speeds and the densities and the mass fluxes that are being found here are just about what we'd like. Now, my point is not to show you something that isn't going to work, but rather to highlight the promise that MHD models have and will have in the next 5 years for understanding the launching of jets or bullets or whatever it is that produces the lobes of young planetary nebulae. What I'm going to do now is go through some paradigms, shaping paradigms. You've all seen at least one of these before, but there are actually 4 of them, and they're interesting to compare and contrast to one another. The simplest one, the one that we hear discussed most often, is the ejection of a clump that comes out of the central star. It just leaves a wake and a lobe behind it. So the arrows here show, in cartoon version, show what the hydro models predict we would find. For the kinematics, I'll say more about that in just a moment. The other related model are jets. And this, when I say jet, I mean a very thin collimated jet, one that doesn't spread out terribly much, and creates a bow shock at the upper end. So here are poster children for these different models. CRL 618 is certainly one of them. It has sets of bullets. And the hydro models that we've generated have shown that to the limit of what we can now observe, we can't distinguish between clumps and jets, at least not terribly well. There are very small differences in in the observables of these two frames right here. So these are the launch of a single clump at about the ejection speed that are measured in the proper motion studies for the fingertips of CRL 618. I want to point out a couple of very common characteristics of all hydro models, not just these. There's something that comes out, but there's an ablation flow that comes off the head and runs backward. And in many cases, the ablation flow is where the mass that came up through the jet is stored in the lobe. There can be a lot of mass in it. There's a weight as well. So the ablation flow is one physical entity. It's created as gas is compressed at the head of the shock or the pump. It squirts off to the side and flows back into the stagnation pocket inside the lobe. There's also a wake which consists of gas that is heated by the shock and which flows along the outer edge of the ablation flow and then kind of collects back in here. There's some ramp pressure in that region. There's somewhat less thermal pressure, but the ramp pressure vectors and the thermal pressures act to broaden this lobe, and that's actually what gives lobes their shapes, that and the density in the ambient medium. I thought to just point out as we go along here that one thing that I have learned from these studies is that Hubble flows may not be for real. I mean, that is, we will measure velocities that increase linearly with distance from the central star and have nothing to do with the brief ejection. All of these ablation flows that we've ever seen, when you just look at the patterns of colors in the arrows, or more carefully map them out, give a V proportional to radius relationship. And these things, the slope of this has nothing to do with the ejection age. It is, as the jet or the clump propagates, the slope of this stays pretty much the same. Another class of models that was pioneered by Rockventra and Lee back in 2003, actually Jorge Canto first proposed this in the context of Hurley Harrow objects, is one in which you have a conical wind, streamlines that diverge. And those streamlines go through the ambient medium that once filled the volume and just push it to the outer edges. And there, the streamlines refract. I'll show you. Oh, here's the poster child, M1-92. But the streamlines come out in these models and refract at a shock, a reverse shock here, where the forward component of their motion is lost to heat, and the lateral component of their motion persists. So the arrows get into the zone here where the mass collects and flow outward where they reconverge in this model to a bright tip at the leading edge. But the point is, the inside is largely empty, not like the ablation flows that you saw earlier. In their paper, they, sorry, so I'm a wrong manager, but I had to change the colors to make the point. Here are the streamlines from one of the figures, and you can see that they're refracted. They just kind of bend right along the reverse shock here. There's an outer shock pushing its way into the AGB winds on the outside, and some material comes through that. This is the V versus radius plot from their paper. And again, you'll notice that in this region here, colored in blue, there's a V, a linear relationship between velocity and radius. Now, a problem that was pointed out by the authors was that the shock speeds here are big enough to rip delicate molecules apart. So it's very difficult to imagine mapping the high-speed flow in molecular emission lines. We'll go back to CRL 618 for just a moment. The movie here is one I showed earlier in Boness. It shows the proper motions of the figures of the jets. They're really moving along. We get outflow speeds of 200, perhaps 250 kilometers per second tops. There's some flows in the inner region here that are more or less coming right at us. So they'll have even higher Doppler shifts than those that are measured out here. It's characteristic of CRL 618, and not many other objects simply because they haven't been studied much, to find iron 2 at the leading edge of the fingers. Iron 2 is excited in shocks, and then molecular hydrogen, here's a molecular hydrogen image in the region down here. This is nothing new. The OMC fingers show precisely the same thing, iron 2 at the fingertips, molecular hydrogen along the edges. The molecular hydrogen in this case was pushed aside by the bow wave at the front of the fingertips when the pumps went through. Now to compare these, I think we've already discussed this. The ablation flows as well as the jet fill the lobe interiors. This is the material that would be radiating, if anything is. It's dense, it has a high emission measure. The radiation would be coming from here, where the arrows are increasing in velocity in proportion to radius. The outer regions here might be seen weakly in shocks. That would be the molecular hydrogen. These are not very fast shocks out here. They're slow enough that the molecular hydrogen in the ambient medium is excited and compressed, but not destroyed. And to compare that to what in this slide called the tapered winds model, the radiating material will be in the walls, not in the center. And so this provides us with an observational handle on testing the two paradigms, comparing the two paradigms. For CRL 618, Cox et al. in 2003 mapped the molecular hydrogen shown here, but not with quite enough spatial resolution to determine whether the hydrogen was in the spine of the lobes or along the fingers. The CO images, this is the most recent one, Rod Bender showed it during his talk, and other people have too, show that the low speed CO is along the edges of the fingers. That's no big surprise. These fingers are embedded in a large molecular shell. And here, maybe, there's some high velocity CO that lies right along the spines of the fingers. I think that's ambiguous, but it wouldn't take long with some deeper observations to settle the issue. Another paradigm is magnetic shaping. So in this case, I illustrate what happens when you launch a toroidal field from the surface of the star, and the winds from the star sweep it up and carry it along. They provide the magnetic fields head outward in a hoop, which constrains the streamlines and actually guides the streamlines towards the central axis. So this is a simulation by Tim Dennis et al. And Adams group, going back to 2009. And this is with no stellar wind, and this is the same set of initial conditions. Sorry, this is with no magnetic field. This was with the magnetic field turned on. And you can just see how the densities are high right along a jet. So what we would expect to find, and other models have confirmed, this is the earlier set by Guillermo and company, that the lobes are long and thin and contain jets running up their spines. Now, one nice thing about magnetic fields is there are enough knobs to twist that you can get a broad variety of morphologies to which you might be able to fit Hubble images. Now let me move on to some other big successes in the last few years. In this paper in 2004, winds were just launched into a network of clumps with ablation flows behind each one of them. And the overall velocity pattern was studied theoretically, and guess what? It's another one of these Hubble flows. There's no Hubble flow in here. The winds are steady. And it's the ablation flows, so the patterns of velocities behind them, which give rise to the patterns that are observed. Very recently, Wolfgang and company came up with this idea of a torus that has holes in it. There's a whole class of preplanetary nebulae that aren't bipolar. They have a very irregular set of shapes. None that I can remember are actually round. They're just messy. And this paradigm, I think, successfully explains the morphologies that we see. Wonderful, wonderful breakthrough. Later, the starfish nebulae take on shapes. You can see them in here. in the models, and you can see quadrupolar flows and other things like it in their simulations. The airlock looked at radiation pressure and instabilities coming from radiation pressure. The radiation pressure of winds flowing into a torus here. And you get networks of figures. This is an alternate explanation for the kinds of starfish nebulae that have been seen for many years. Here in this APM meeting and throughout the literature are increasing numbers of simulations of mass transfer and binary orbit systems. Another fabulous success of the hydrodynamics. I'm not going to review them here. We've heard about them in earlier talks. Now for the work that we're doing using AstroBear. I'll just review this very quickly. It's a pleasure to be able to change the configurations of the external density and the geometry of the flows. And you learn so much. So this is a cold, thin jet ramming up into a medium that has a torus and a 1 over r squared AGB wind in the background. The density is here. Temperatures are on the right. And orange here, yellow, is about 10 to the 7th degrees. You can calculate the shapes. You can see the ablation flows coming off the edges. You can play with the parameters of the jet. In this case, what's significant is that the jet has soft edges, and the ablation flows that come off can just stream right back. This is just like the flow over an airplane wing. We curve the front end of the airplane wing, we control the flow patterns. We see the same thing going on here. And this, I think, is a wonderful way of explaining so many of the cylindrical or pre-planetary nebulae. We also get a lot of information from the program on velocities. You've seen this sort of thing before. And on the dominant pressure, so that you can look into the models and understand why they and how they evolve as they do. I'm going to skip on. We can play with the jet speeds, and what we find is that at least with this external density configuration, we don't exactly get scaled lobes. They look very similar to one another, but the ratio of this speed to the forward speed is 0.22. In this case, it's lower, it's 0.17, and in this case, it's 42 over 3, whatever that is. You also see in here, you see the jet, you see the ablation flow coming from it. You see this zone out in here, which, as I mentioned earlier, has some ram pressure left over from when the jet ran through the medium and pushed things sideways, and also some thermal pressure, especially down at the base here, which opens the base up. What you also notice in all of these models is that there's compressed gas down in here along the outer edge of the wake. No surprise there, absolutely none. But if you like making nested lobes, that's the way you're going to get the outer one. And the inner one will come from here. So now we've been playing with M29. I guess many of us have been chasing M29 more or less as a nemesis for the last 20 years, trying to figure out how it works. And I wouldn't say that we're there quite yet, but we're coming up. So what you see here is kind of a spreadsheet of data collected together and gone. There are inner lobes here, there are outer lobes. It's really easy to make the outer lobes, and it's not that hard to make the inner lobes, but what's very difficult to do is to make these little knots that sit on the symmetry axis. And an HST image is separated by 5 years. We find no proper motions in those things, just nothing. Which means no hydro model is going to be able to produce them because they're static. There's a lot of other information in here. We won't review it all. It's very nice that there's infrared data on both. Let's see which is which. This is iron 2 along this line of this slit. Molecular hydrogen here. The molecular hydrogen is coming from the outer edges and doing exactly what you'd expect as the ambient medium is pushed aside by the wave. Now what we're trying to do is we're not going to be able to create these knots in here. These are really mysterious. But what we might be able to do using the code is to understand the morphology around them. So you see this bulb-like shape. It's in the inner lobes. Another over here. The knots that are stationary. so what we've been doing the last week or so is adopting the champagne cork model, where whatever launched these things a long time ago, launched them actually rather slowly, but the spray of stuff came out behind them and interacts with the nuts. So the program, as it now runs, doesn't allow us to mimic this very well, but well, here's some examples of an almost stationary plum with a mass of about 10 to the minus fourth solar masses and a diverging wind that slips up from behind it. And the ablation off the edge of the plum forms these little curlicues. So we've at least got these things down. Now we need to mess with the parameters of the diverging wind until we get nice smooth lobes that resemble those in here. I'll just point out that the bulbs and the lobes are shocked. We're looking at either two emission here contained at Gemini. So I'm going to get through some of this stuff. The group in Rochester is now coming up close to releasing the